Today we are going to discuss about the RC coupled amplifier. If the time permits, we will discuss about the public address system also. And this RC coupled amplifier is an important topic in your basics of electronics engineering, because the same theory and applications of this particular circuit is going to be done in the ESL 130 electronic workshop also. So now is the workshop session. In the workshop session, we have to learn the working principle of RC coupled amplifiers and how the circuit is set up and all those things. Of course, that video will be separately given to you, and that will be uploaded to Moodle. So today we will see how this RC coupled amplifiers are set up and how these amplifiers are working. In the what are the important aspects and things to be noted while we learn about RC coupled amplifiers. Okay. Now, what is an amplifier? An amplifier is an equipment which receives the input signal to perform signal amplification. Amplification is the process of increasing the amplitude of the signals. Amplifier derived from external source, power from external source, and uses it to boost the input signal strength. Amplifiers employ active devices like transistors. Transistor is an active device that we have already learned. A DC source used to bias active devices supply the additional power. All details of the signal waveform is preserved. The output waveform is an exact replica of the input waveform. Okay. Now, what are all the amplifier characteristics? An amplifier has got the following essential characteristics. What are those characteristics? The first characteristic is the gain of the amplifier A. Gain A. So we will see each of these characteristics separately. Then second characteristic is the input resistance Ri. Then output resistance Ro offered by the transistor circuit, amplifier circuit. The bandwidth B. So these are all the four important characteristics of an amplifier. That is amplifier gain A, input resistance Ri, the output resistance Ro, and the bandwidth P. So what is the gain of an amplifier? The gain of an amplifier is the amplifying capability of an amplifier. Gain is the ratio of the output signal amplitude to the input signal amplitude of the amplifier. So output signal amplitude means that is in volts. That if it is a voltage signal, then it is in volts. Of course, the signal will be very small, of the order of some millivolts or so. So that output to volt, that is amplified signal voltage to the input signal applied to the amplifier. So I told you the gain is the ratio of output signal amplitude to the input signal amplitude of the amplifier. And since it is a ratio of two amplitudes, so this is a dimensionless quantity. Dimensionless quantity means there is no unit. So it is denoted by a letter, by a number, usually say gain 180, like that. Okay. So it is a dimensionless quantity, and this particular characteristic gain is denoted by the letter A. If it is a voltage gain, we will suffix V also along with this one, that is AV. If it is a current gain, then it will be AI. If it is a power gain, then it will be AP, like that. Okay. The gain of the amplifier should be very large. For a common emitter configuration, the gain of the amplifier must be very large, because that is the main reason why C configuration is used as an amplifier, especially the voltage amplification and for in general audio amplification. We will come across all those things. The gain of the amplifier may be either voltage gain or current gain or power gain. So what is meant by voltage gain? Voltage gain is the output voltage VO divided by the input voltage. It is the ratio of the output voltage or output voltage amplitude of the signal to the input voltage amplitude of the signal. Okay. Then current gain is also AI is equal to I0, I output by I input. I means I output, II means I input. Similarly, power gain is AP is denoted by the letter AP, but power gain is denoted by the letter AP, and that is equal to the output power divided by the input power, and that is numerically equal to the voltage gain into current gain. So what is meant by voltage gain? That is the output voltage divided by input voltage, that is represented by A suffix V, AV, and A is the current gain. So AP, that is power gain, is equal to AV into AI, right? So the VI is the input voltage, LI is the input current, PI is the input power, VO, V, and IO, PO are the output voltage, current, and power. Okay. Now, the gain of the amplifier can be represented or it can be expressed in logarithmic measure. Usually, the gain of the amplifier is large. I told you the gain of the amplifier is large. So usually it is represented in bell. So bell means that is a very large quantity. Usually, in order to represent the gain of the amplifier, we rely upon the decibel. Decibel means 1/10th of a bell. Bell is a very large number, a very large representation of the gain of an amplifier. Then we usually use decibel for the purpose of expressing the amplification or amplify gain of the amplifier. Gain is denoted by the tray I told you. Then voltage gain in dB is given by the equation dB. Voltage gain is equal to 20 log AB. I told you the gain is represented in logarithmic measure. So logarithmic measure means the value will be logarithmically done, that is 20 log AB. So it is represented in logarithmic representation, that is 20 log AV. Then current gain in decibel is equal to 20 log AI. Power gain in dB, that is power gain in decibel, is given by, that is 10 log, not 20 log, 10 log AP. There is a specific reason for this one. If you are interested, you can go through a textbook and get this result. Otherwise, we just learn it like that. Okay, because we don't waste time for why which is represented as 10 log AP and all. It is nothing but the voltage gain into power gain, from which only you can very easily understand why is it so. Okay, so power gain in dB is equal to 10 log AP. 10 log AP. If the gain is less than 1, then if the gain is less than 1, what does it mean? The dB measurement of the gain, that is gain in dB, is negative. If it is less than 1, means it is negative quantity. So the dB gain in dB is negative, means it is not an amplification, it is an attenuation. If the signal is if you give the input signal to the amplifier and if it is attenuated and you are getting a reduced signal, that is attenuation. Attenuation means that when you give an input signal and if it is attenuated, means the output of the signal will be reduced one. It's a reduced one. So amplification means that is actually the amplifying version of the input signal, right? So if the dB gain is negative, less than 1, then it is an attenuation, and we we get the reduced signal, what's called the attenuation. That is opposite of the amplification. Now we will see what is the input resistance of an amplifying circuit. The total equivalent resistance at the input terminals of an amplifier is called the, or that is known as the input resistance, or that is usually the input resistance of the amplifier. The total input total equivalent resistance offered by the input circuit of the amplifier. That is what is the total resistance offered by the amplifier at the input side. That is what is called the input resistance, RI, in ohms usually. That may be represented in ohms or kilo ohms sometimes. Okay. So it is nothing but the ratio of input voltage to input current. So the input resistance will be obtained by the ratio of input voltage to the input. Value of the input resistance of the amplifier should be very large. You will see why is it so. So input resistance must be very large. Okay. So what about the output resistance? The total equivalent resistance at the output terminal of an amplifier, and that should be very large usually. It should be, and this value of the output resistance of the amplifier should be very small. Should be very small. Why is it? Weight should be very small. That also I will tell you. The input resistance is very large, means the current taken or the input current taken by the amplifier for its own operation will be very large. The amplifier is supposed to it is actually meant for amplifying the signal. So it should only take a very small value of current for its own operation. So whatever is the input signal obtained on its input circuit must be amplified and available at the output side. So that is the purpose of amplification. So in that case, the device itself should take only a very small current. That is why the input resistance of the amplifier is usually designed to be a large quantity, usually 1 kilo ohm or 2 kilo ohm, like that. Okay. So what about the output resistance? The output resistance of the amplifier must be always very low, because the output resistance means that is the resistance offered by the output side of the amplifier. Output side of the amplifier means where the output signal will be available, isn't it? Where the output signal will be available. So the output signal, that is output resistance, means that is the resistance offered by the, that is the equivalent resistance offered by the amplifier at the output side, that is at the output, and that resistance must be small. Usually, why? Because when you connect the output side of the amplifier to the next input stage of the other amplification stages, because a single stage amplifier will be having only one stage, but usually every amplifier will be having multi stages. Sometimes the signal amplified by single stage may not be sufficient enough. In that case, we have to amplify first stage amplification to another circuit of same amplification, and so that that signal output of the first stage will be again amplified by the second stage. So that at the output side you will be getting a very good amplification. That is, the second stage output will be in a very good amplification. So necessary and sufficient amplification will be then taken place there. So that is why in order to connect the first stage with the second stage, of course, there must be a impedance matching between, or there must be or in other words, the amplifier has to drive the load. What is the purpose of the amplifier? The purpose of the amplifier is to drive the load connected at the output side of the amplifier. So that load has to be driven by the amplifier. So that is possible if the amplifier output resistance, that is output resistance offered by the amplifier, must be very small, so that it can drive the subsequent stages of amplification or subsequent loads connected to the output side of the amplifier. If the output resistance is smaller than the load resistance, that is the reason I had told, more voltage will be transferred to load and the output of the amplifier. If the output resistance is smaller, then it can drive the load very easily, and so that what happens, more voltage can be transferred, because transistor's main purpose is to transfer the signal from the input side to the output side, isn't it? So if the output resistance is smaller than the load resistance, more voltage can, or more signal voltage. More voltage means more signal voltage output will be transferred to the load as the output of the amplifier. Okay. Then next is the very important characteristic, what is called the bandwidth of a transistor amplifier. For any amplifier, there is a bandwidth. What is the bandwidth? Bandwidth is actually the range of frequency in which the amplifier functions as desired, or it is the range of frequencies for which an amplifier gives a desired gain. So every amplifier is meant to work within certain ranges of frequency. That is, the amplifier will be amplifying the signal very effectively within certain frequency ranges. So in that case, of course, there will be a smaller frequency ranges and there will be a higher frequency range. So every amplifier is giving, or every amplifier is supposed to, or is supposed to give almost the same amplification throughout certain frequency ranges. The frequency range at which the amplifier gives the desired gain, desired voltage gain, desired current gain, and desired power gain. And that range of frequency is called the bandwidth of the amplifier. For CE amplifier, usually the bandwidth is actually that particular amplifier is meant for amplifying audio signals. So it is used as an audio amplifier. Usually the bandwidth will be well within 20 hertz to 20 kilohertz, because that is the range of frequencies for audio signals. Audio signals are actually the signals which are ranging from 20 hertz to 20 kilohertz, or 30 hertz to 30 kilohertz. That is the range of frequency. And voltage for other voltage amplifications and all, of course, the range of frequency will be like this. There is a frequency range within which the transistor will be giving a very good gain, or the desired gain. So that is the bandwidth. Okay. Now, now we will see what is a common emitter amplifier. So first, before we discuss about the common emitter amplifier, we should know what are the common emitter characteristics. We have seen the input characteristic and output characteristic of common emitter amplifier. So in a common emitter amplifier, what are the three regions of operation? The three regions of operations are the cutoff region, that is the off state of the transistor. Then there is a active region, that is the amplification region of the transistor, and there is a saturation region, that is the on state of the amplifier. So these three region of operations are there in a common emitter configuration. In a common emitter configuration, we have three regions of operation for the amplifier, or three regions of operation for the common emitter configuration. That is the cutoff region, then active region, then the saturation region. Or this active region is the region which are very commonly used for amplification purposes. For the main purpose of the active region of a common emitter configuration is for amplification. That is why common emitter configuration is very widely known as common emitter amplifier. Common emitter amplifier. And if you are connecting a common emitter amplifier with an RC coupled network in order for some other purpose, of course, there are certain purposes for connecting the resistor capacitor network. So that particular network which connects with this common emitter amplifier will give us a RC coupled common emitter amplifier. RC coupled common emitter amplifier. Why we say RC coupled common emitter amplifier? The common emitter configuration is connected with RC network in order to bias, stabilize, and also to compensate for the signals and all those things. So certain bias condition has to be satisfied. Of course, the system has to be biased before amplification and all signal amplification. Then the system, the common emitter configuration has to be biased properly by giving certain potential, that is polarity, certain potential with proper polarities. That is what is called a bias, isn't it? So that particular biasing should be done before we operate it as an amplifier. So we should know these three regions of operation, out of which we have to see what is the behavior of the common emitter configuration in the active region. Or our concern is, or our interest is to know the operation of the CE configuration or CE configuration in the active region of operation of the transistor amplifier or transistor. The active region of the transistor in the CE configuration will give an amplified signal if you give an input to the common emitter configuration. If you give a signal input to the common emitter configuration in the active region, the signal will be amplified to a certain desired level with certain gain, voltage gain, current gain, and power gain. So that is why common emitter configuration is very widely used as a common emitter amplifier. The output characteristic of common emitter configuration of an NPN transistor is the relation between the output voltage VC and collector current IC for a constant base current. That we have already seen the output characteristic of the common emitter configuration. What is the output characteristics? That is the relation between the output voltage VC and collector current IC for a constant base current. That we have already seen in the output characteristic. The output characteristic of common emitter configuration of the NPN transistor, which is shown in the graph, I will show you. And this particular configuration has got three regions of operation, that is the cutoff region, the active region, and saturation region. Okay. And the common emitter configuration can be used as an amplifier when the transistor is operated on its active region of the output characteristics. So in a common emitter configuration, that configuration can be, that common emitter configuration can be used as an amplifier when the transistor is operated in the active region of the output characteristic, where we actually see all these regions. The region of operations are seen on the output characteristic, isn't it? That is the plot between VCE and IC for a constant IB, isn't it? VCE means collector emitter voltage, IC means collector current, IB means base current. For a base current, if we plot for different VCE, what are the changes in IC? So that is the plot between the VCE and IC curve for a constant IB. So that is the output characteristic. In that output characteristic, we can see all these three regions of operation, out of which the active region of operation is of our interest because that region is giving us the amplification of signal, right? So this is the output characteristics. So in this output characteristics, when IB is equal to 0, there is no base current. It means that if you apply VCE, then you will not be getting an IC as such because there is no IB. The IB is the input current, and that input current is 0 means there is no amplification as such. But instead of that one, there will be a very small leakage current from collector to base. That is what is called the collector to base leakage current or the current due to minority carriers, because collector to base is a reverse biased junction for a C configuration. For a C configuration, input is actually through between the base emitter and output is actually given, output is taken from collector to emitter. But the base emitter junction is forward biased, collector base junction of the C configuration is reverse biased. So when IB, that is base current, is equal to 0, in that case, there is no collector current, appreciable collector current. The only current flowing through the collector is the leakage current due to minority carriers because the collector base junction is reverse bias. That we have already seen. Now, if you increase the base current, of course, you will be getting a graph like this for different VCE. VCE is increased. Of course, IC is almost constant. There is a not appreciable change. That is why this curve is almost parallel to the exact. Similarly, you will be getting for another IB. Again, the current increases and reaches to a point. From where onwards, the current IC is almost constant like that. So you will be getting a set of graphs like this. And this is what is called the output characteristic. That is the plot between VC and IC for constant IBs, different constant IBs like this, isn't it? And in this particular graph, this IB is equal to 0, where the transistor is in the off condition. The transistor is in the off condition because there is no IC. So transistor is in the off condition. And this particular region is called the cutoff region. And the region where the VCE takes a very small value after certain ranges of IB. When your IB is going on increasing, at certain value of IB, the IC will be increased much. But accordingly, the output voltage VCE will be reduced back. Only the current is flowing through the junction. And that particular condition is what is called the on state of the amplifier or on state of the C configuration. And that on state is actually the state at which there will be collector current, but the collector emitter voltage will be very much reduced at that particular collector current. And this range or this range of operation or this region of operation of the transistor is called the saturation region, or we say that the transistor is getting saturated. We don't interest on this region and this region. This is the cutoff region and this is the saturation region. And these two regions are meant for operating the transistor as a switch, right? Transistor as a switch. What is the purpose of a switch? When you put on the switch, there will be current flow. That is on condition. When you put off the switch, there is no current flow. There is no current flow, isn't it? That is the off condition of the switch. So if you want to work the transistor as a switch, then you have to operate the transistor between the cutoff region, in the cutoff and active region. If you operate the transistor in the cutoff region and in the saturation region, not between. Between what is that? Between is the cutoff and active is, and between cutoff and saturation is active region only. But between cutoff and saturation region, we have active region. But if you operate the transistor in the cutoff region and the saturation region, then the transistor will be operating as a switch. But our aim is not to operate it as a switch. It can be operated as a switch if we maintain such conditions here, isn't it? So, but our aim is to operate this transistor as an amplifier. So, our interest is to know about the characteristic features of this amplifier in the active region. That is why every transistor C configuration can be used as an amplifier if it is operated in the active region. That's why I have taken this output characteristic also along with this one. Of course, you need not always try and learn this like this, but you should understand. These are all the results. These are all the reasons why we are very much interested on the output characteristic of the transistor and in the C configuration. Okay. Now we will see the biasing the transistor. Why should we bias? What is meant by biasing? Biasing is the application of a DC voltage with proper polarity and magnitude to the transistor circuit to operate it as an amplifier. If you want to operate a transistor as an amplifier, you have to bias the transistor with the proper polarity. What is meant by biasing? Biasing is giving the DC voltages to the junctions of the transistor with the proper polarity. What are those junctions in a C configuration? There are two junctions. One is the base emitter junction, that is the input side. The base emitter junction, that is the input side. And that junction must be forward biased because that is a PN junction that must be forward biased. That is the input PN junction. That is the forward biased junction. And what is the other junction? That is the collector base junction. And for a C configuration, collector base junction must be always reverse biased. And this will be always same. The base emitter junction of a C configuration must be forward biased, and the collector base junction of the C configuration must be reverse biased. This condition is the biasing condition for C configuration. Okay, so now you know what is meant by biasing, why we give biasing, and why we are giving biasing. Due to biasing, certain voltage and current conditions are established for the transistor. And these are all called operating conditions. Why should we give biasing voltages to the transistor amplifier or for the transistor circuit in C configuration or any configuration? Because if you bias the transistor with certain voltage, then certain current conditions are established. Certain voltage and current conditions are established in the transistor, and that are what is called the operating conditions. For a C transistor, I told you the biasing to be given is the base emitter junction must be forward biased and collector base junction must be reverse biased, and that are the operating conditions to be preserved for operating it as an amplifier. Okay, and these operating conditions are called DC operating point or DC quiescent point or Q point. About whenever you hear a transistor has got a Q point or quiescent point or DC operating point, it means that that is actually the parameter, that is actually the operating condition of an amplifier when it is biased. Why it should be biased? Because we want to operate that particular device as an amplifier. So if you want to operate the device for some other useful purposes, first you have to bias the transistor. For amplification purposes, what you have to do for a C configuration, for amplification purpose, you have to bias the base emitter junction, forward bias, then collector base junction, reverse bias. That is the operating condition of the transistor in the C configuration. That is why it is called C amplifier. Okay. Then I told you the transistor must be operated in the active region of operation of the device. Then for a common emitter amplifier, the operating point must be fixed at the center of the active region. That is, we have seen this is the active region. And for the operation, for the satisfactory and very desirable operation of the amplifier in the C configuration. So in order to use it as an amplification amplifier, in order to use it as an amplifier, we have to choose the DC operating condition almost at the middle of the operating region. This is the operating region, isn't it? So almost at the middle of the operating region means we will just analyze the circuit by drawing a DC load line like this. DC load line like this. So this load line represents the DC condition for the or DC operating point to be fixed in the active region. So that whenever you give an input signal at the base emitter junction, that signal will be traversed only at that particular region of this active region. So at the particular space or at the particular region of this active region only, that signal will be traversed. So if you give the alternating signal at the input side, then that alternating signal will be amplified and that will be available at the active region of the, or that will be amplified at the active region of operation of the transistor, isn't it? So that is why we fix an operating point almost at the middle of this, because the signal should not be deteriorated or the signal should not be distorted. Whenever you give a signal for the amplifier in order to amplify it, then that signal should not be disturbed. Whatever is given input, that should be amplified and given at the output side without distortion. So we should get a distortion less output. Then only whatever is the input given, if it is an audio signal, then amplified version of the audio signal must be available. Otherwise, what happens if there is a distortion? It means that the output will be different. The sound effect will be different. If you play an audio record of S-DOS, then if the amplifier you heard this particular audio signal is having distortion, and at the output side if there is distortion, the signal will be heard, and that will not be heard with the distortion. It will not be the actual, the sweet tune or sweet tone of his thus. It will be somewhat different. It may be some female voice, like, or such type of errors will be there occurring there due to the distortion. So that should not occur. That's why the amplifier should give a faithful amplification. In the terminology of amplification, there is a term called faithful amplification. Every amplifier is supposed to amplify the signal faithfully. There should be a faithful amplification for the amplifier. There should be a faithful amplification for the amplifier. In order to have a faithful amplification, the operating point or DC condition must be maintained in such a manner that the operating point or quiescent point of the amplifier must be made between the active region, that is almost at the center of the active region. Okay, that is what is meant with that particular word, that particular sentence. Or the operating point must be fixed in the center of active region of operation of the transistor. Okay. Now, to fix the operating point at the middle of the active region of the transistor, we need a biasing circuit. So, in order to fix the operating point at the active region, center of the active region, we need a biasing circuit. That is the need of the biasing circuit. So, we will discuss about the need of the biasing circuit. What is essentially the need of the biasing circuit? In order to fix the operating point at the middle of the active region, the first need. The second need is to stabilize the collector current against the temperature variation. So, transistor is essentially a device having two junctions. The junctions are always subjected to temperature because it is carrying power, isn't it? It is carrying power. The output side of the transistor, that is the on the collector-based junction. Of course, there is a high current flow due to amplification, isn't it? So that actually causes to have a high heat dissipation on the collector side. So this temperature at the collector-based junction may be increased or decreased depending upon the collector current, isn't it? So this temperature variation should not affect the operation of the transistor, or that should not affect the gain of the transistor. So that is why we design a stabilization circuit, or we design a biasing circuit which stabilizes the collector current in such a manner that any variations in the collector current should not increase or decrease the temperature very much. Or the temperature variations at the junctions can be controlled, or that will be always stabilized by the biasing circuit. Okay. Then what's the third need? To make the operating point independent of the transistor parameter beta. What is the transistor parameter? Beta. Beta is the voltage gain, or beta is the voltage gain or current gain, isn't it? For a C configuration, beta is the voltage gain or current gain. Voltage gain AV, that can be represented in beta, or current gain IP, I, that may be also represented in beta. Okay. So the you can usually the current gain, that the transistor beta, that is always there. That should not have a direct linkage or direct connection with the operating point. Or the operating point, that is the operating point and the operating region of the transistor must be such that it should not have a dependence upon the parameter beta. Of course, the input signal will be amplified with the corresponding gain which is available with the transistor circuit. But that gain, beta, so what is it? The operating point must be always independent of the transistor parameter beta. So that, why is it so? Why should we have this particular need here? Because suppose if you are using the transistor in the amplifier circuit as an audio amplifier or a voltage amplifier, suppose due to continuous operation of the amplifier for different purposes in the amplifier circuit, so aging will be occurring, isn't it? The transistor will be having aging, so that the component of the transistor may be getting damaged something. So in order to use the same device as an amplifier, then you have to change the transistor which is used as the amplification, which is used for the amplification purposes. So what will you do? You will be selecting a transistor which is available to you, that will be having some transistor beta. Of course, that beta may not be always same. Sometimes initially you have a transistor with beta 60 or 70. Then the second time when you replace the transistor with a new one, it may not be because you are the market you may not be you will not be in a position to get or available with a beta which is 60. In olden days, of course, that may be there, but now the transistor technology has been increased developed that much. That's why we have a new transistor having a beta which is 150, 200 like that. Okay, so the same beta transistor with beta, that is the new transistor with the beta 100 or 150 can be used for the purpose of amplification in the same transistor audio circuit. Why? Because the operating point of the transistor will never change. It is as it is. Once it is fixed and once it is designed and set up and fixed, it is made as it is. Because the transistor beta may not be have a direct engagement with the operating point. Because the transistor is already biased. The operating point is already fixed in the design itself. So it is not in connection with the transistor beta. Beta is different. So it will not be affecting the operation of the transistor. Or otherwise, we can say that with the new transistor, which is connected to the or which is used for replacement of the old one, will make the transistor operating in the earlier manner. The very similar to the earlier, maybe some with the better output because the beta is somewhat increased here. So with a certain output increased. Okay, so in order to replace the transistor, if beta is independent of or the operating point is independent of the transistor gain, then of course you can use replacement of transistor very easily because the operating point is independent of beta. And that is the main reason. And of course, to maintain the operating point stable by keeping IC and VC constant so that the transistor will always work in the active region. So since the biasing circuit always maintain these three conditions or these three needs are satisfied to fix the operating point at the middle of the active region, to stabilize the collector current against the temperature variations. Of course, the temperature will vary definitely, but that will not reflect upon the collector current and the operation of the transistor must be stabilized. And to make the operating point independent of the gain of the amplifier or gain of this transistor used. So if these conditions are satisfied, then the operating point will be always kept well within the active region of operation for a stable IC and VC of the transistor. IC and VC means collector current and collector emitter voltage. That is output, that collector current and output voltage of the transistor is stabilized. Okay. So for doing this purpose, for doing the biasing of the circuit, we have the techniques which are used in the transistor circuit. What are those techniques used for biasing the circuit and stabilizing the circuit? We use a stabilization technique in the circuit. And for maintaining the or for making the collector current respective of the temperature variations, we have a compensation techniques also. These two techniques or these two circuits or circuit components or circuits which are arranged with the C configuration makes the transistor operating point almost within the active region of operation. Okay. So now what is the stabilization technique? Stabilization technique refers to the use of resistive biasing circuit which allows the base current IB to vary so as to keep the collector current IC relatively constant with the variations of ICO, beta and VB. We know that when IB increases, definitely IC must increase, isn't it? Beta into IB is the IC for a C configuration. And we have to keep the collector current IC relatively constant with the variations of ICO. What is ICO? ICO means when the IB is equal to 0, there is a collector to base current when collector to base region or collector to base region of the transistor when the base current is equal to 0. Base current is 0 means the base is open circuited, isn't it? So that is why it is called ICO, or sometimes some book you can see it is ICEO. In order to say that, in order to know it as, or in order to symbolize it as I collector emitter configuration with base open. That is ICEO. Okay. So ICO or ICEO. That is relatively and so that the IB variation of IB must be always independent of this IC ICO, beta, and VB. What is VB? VB is the base emitter voltage, input signal voltage, and that is numerically, usually numerically just more than 0.7 volt is enough, because that is the cutting voltage for a base emitter junction when it is forward biased for a silicon transistor. Then what is meant by compensation techniques? Compensation technique refers to the use of temperature sensitive devices such as diodes, transistors, thermistors, etc. And transistor is a temperature sensitive device. I told you in the two junctions there will be temperature dissipated. So it's a temperature sensitive device. So in that case, of course, the circuit must be always such that the temperature variance should not affect the operation of the transistor or the operating conditions of the transistor. That is the main purpose of the compensation technique. Okay. And this circuit that is resistive and that biasing circuit will give compensating voltages and currents to maintaining the operating point always well within the active region of operation. Now there are different kinds of biasing techniques used in CE configuration and other configurations, out of which for CE configuration the worldwide and very universally accepted method is the voltage divider bias or self bias. So that is why you need to learn what is meant by voltage divider bias and what is meant by self bias. Okay, and this is the most widely used biasing technique or biasing network for a transistor amplifier, especially in C configuration. In C configuration, this is the main technique used for biasing, voltage divider bias, or sometimes it is called self bias. In this biasing network, an additional resistance R2 is connected between base and ground as shown in the figure. So this is the biasing network. So this is the bias, this is the transistor, and this is the transistor resistance RC. That is the transistor, the resistance connected at the output side of the, that is collector side of the transistor. And VC is the collector emitter voltage, that is the output voltage, that is numerically equal to, that is the voltage between collector and, that is the voltage raised between, or that is the voltage developed between collector and emitter, that is the output voltage. And this RE is the emitter bypass capacitor. We will learn it. What is this resistor? What is this resistor? This is the emitter resistor, and that is the resistor connected in series with the emitter circuit, or in series with the emitter circuit. And what is the purpose of the resistor? You know, this resistor actually makes the stabilization. This emitter makes the stabilization for, or the compensation of temperature variations and all those things, isn't it? Or that is the resistor, emitter resistor. And VB, that is the input voltage. That is the VB is the biasing voltage given by this VCC. VCC is common to all. The VCC is common. That is the voltage between the common VCC positive point and the negative point, or the earth point. Negative point, earth point. This is the earth point, or negative. This is the positive. So between this, we will give the VCC, and this VCC will be reverse biased between collector base junction. Here, this is positive. This is positive. This is negative. And P N. This N is connected to positive, and this is P. So this is reverse bias. What about this one? Here, this is VCC is dropped across this one, and this dropped here. So this is positive. So this is P. So this is P, and this is N. So this PN is connected properly with the biasing and all. So this will be, this base emitter junction must be, what will be forward bias. So for, in other words, for C configuration, base emitter junction must be forward bias. Collector base junction must be reverse bias. And that ensures this connection. And here this R1 and R2 are the biasing network. R1 and R2 are chosen in such a manner that R2 will be developing a voltage. R2 is the resistance between the base emitter junction. Resistance connected between the base emitter junction is the R2. And the voltage dropped across the junction, or voltage dropped across the resistor R2 is the voltage applied between the base and emitter junction of the transistor, right? And that is ensured with this R1 and R2. The name voltage divider came from the voltage divider circuit formed by resistance R1 and R2. That is why this particular circuit is called voltage divider, because the biasing, or the biasing of the base emitter junction, or the forward biasing of the base emitter junction, is ensured by the voltage drop across the resistance R2. Or in other words, the forward biasing of the base emitter junction is ensured by the proper selection of the resistance R1 and R2 as the resistance voltage divider network, or resistance voltage divider, or generally the voltage divider. So this current which is flowing through R1 will be I1. Since IB is very small compared to I1, so almost the same I1 will be flowing through this one. This will be of the order of some milli or even such a very small current. So compared to the value of I1, this current is very small. The current taken by the base is very, very small, right? So that almost the same I1 will be flowing through this one. So I1 into R2 will be the voltage drop across the fan, and voltage will be sufficient enough to make the base emitter junction forward bias. Or this resistance divider network or this voltage divider biasing network should ensure the base emitter junction forward bias for the operation of this NPN transistor as an CE amplifier. So when this particular resistance along with some capacitors connected on the output side gives an RC network for the amplifier. That is why this particular setup is called resistance capacitance coupled RC or resistance capacitance coupled common emitter amplifier. Okay, we will see. This is only just for knowing, giving you the understanding of voltage divider biasing. We will come across the real operation of RC coupled amplifier now. The operating point can be made almost independent of beta. I told you why the operating point must be independent of beta. That I have already explained to you earlier. Now we will see the voltage divider bias or self bias. What is the voltage? The voltage drop across R2 forward bias the base emitter junction. This causes the base current and hence the collector current point the zero signal conditions. Actually, when we create the DC operating conditions, there is no signal applied, isn't it? There is no signal applied for biasing the transistor. Only the voltage applied is the DC voltages for just making the transistor with sufficient operating conditions. That is base emitter forward biasing and collector base junction reverse biasing. So that a DC condition is maintained before operating this particular configuration as an amplifier. So this causes the base current and hence collector current flowing this zero signal condition. So under zero signal condition, when there is no current flowing through that base, only a very small DC current flowing due to the application of the base emitter voltage, VB, isn't it? So there will be a very small current. Suppose that current flowing through the resistance R1 is I1. As the base current is IB, that is very small. Therefore, it can be assumed with reasonable accuracy that current flowing through R2 is also I1 because IB is very small compared to I1 or current through resistance R1 and R. Right? So IB is very small because that is the base current that is usually very, very small. And with reasonable accuracy, we can consider the same IB flowing through resistance R2 also here. The same current I1 flow through R2 also. That is why I1 is shown here as I1 here. Of course, it is really equal to I1 plus IB. But IB is very, very small, almost nearly very small quantity compared to this I1. That is why this I1 is almost same as this I1. Or if you have this I1 to be, if you consider this as I2, then I2 will be, strictly speaking, I2 must be I1. This I1 plus IB, isn't it? This I1 is flowing. No, I1 minus IB, not I1 plus. I1 is coming here and IB is flowing here. It is away from, at the junction, if you apply the current below, I1 is meeting and it is divided into I1, that is I2 and IB. So actually I2 is equal to I1 minus IB, isn't it? That is equal to I1 minus IB, or that is numerically equal to I2 must be IB. But this IB is almost equal to zero. Almost equal to zero means very small milliampere, such a very small current is flowing. So it means that almost you can consider I2 to be equal to IB. That is what is meant here by saying this one. So the voltage across R2 is V2 is given by VCC into R2 divided by R1 plus R. The voltage V2 ensures the forward biasing of the base emitter junction of the transistor. Now applying the KVL at the base. Basically, if you apply the KVL at the base, so KVL at the base, what happens here? VCC is equal to this particular current, that is VCC, V2 is equal to VCC into R2 divided by R1 plus R, that we know. And the V2 is again equal to VB plus IER, that we have seen. What is V, what is that V2? V2 is the voltage across R2, isn't it? If V2 is the voltage across R2, that will be numerically equal to VB plus IER, isn't it? VB plus IER. And I is also numerically almost equal to IC because IB is very small, isn't it? So that we will see here. V2 is equal to VB plus IRE, and I is numerically equal to V2 minus VBE by RE, or I is almost not equal to, it's almost equal to IC. So almost IE difference IC will be very small. So that's almost equal to IC. Therefore, IC is equal to V2 minus VBE divided by RE. Otherwise, what we have to write down? IE is equal to IC plus IB, but IB is far less compared to IC. That's why IE is almost equal to IC. So in that case, IE is equal to IC means IC is equal to V2 minus VB by R, because IE is equal to almost equal to IC, isn't it? So in that way, you can find out IC, and it is clear from the above expression that IC does not at all depend on beta. Here there is no beta term. IC is equal to V2, that is voltage across resistance R2. That is VB plus IER, isn't it? V2 minus VB. VB is also that cutting voltage, VB, isn't it? Plus V2 minus VBE divided by RE, that is the resistance at the emitter lead or emitter, and resistance comes at the emitter lead, isn't it? So IC depends only, it does not depend upon this parameters, though it depends upon VB. Why is it depends upon VB? Because VB actually represents the current IB, whether it is increasing or decreasing. If VB is slightly increased, IB will be increased. But still then, V2 minus VB by RE will be almost equal to IC, because IB is very small. Follow my point. So, but in practice, V2 is far greater than VBE, so that the current IC is practically independent of VB. So, for practical purposes, V2, that is voltage across resistance R2, that is here, will be far greater than VBE. VBE from 0.5 or 7 came down. But what about this? This will be of the order of some 5 volt or something like that. Such a big voltage as far as VBE is concerned. So that is why IC is, in the circuit is almost independent of transistor parameters. IC is not dependent on VBE also. So we say that IC depends upon IB and IB depends upon VBE. But here you have to see, IB depends upon VB, and of course it is independent of, it is depending on beta, and IC depends on VB. But when we consider the value of V2, that will be far less than VB. So VB can be neglected sometimes. So what is IC? IC is equal to V2 divided by R. And again, you can see that IC is independent of VB. Right? There is no VB term here. VB is very small compared to V2. Okay, so that is meant here, like this. So what in effect what happens? IC in the circuit is almost independent of transistor parameters. So the transistor parameters are VBE, beta, IB. So IC is almost independent of all these 3 parameters now. We have seen. So that is why this circuit with the voltage divider bias gives a very good stabilization and ensured with the voltage divider. And that is why good stabilization is ensured with the voltage divider bias. So that is why we prefer voltage divider bias compared to any other kind of bias used in transistor configuration. So voltage divider bias is very commonly used in almost most of the common emitter amplifier applications, voltage amplifier or audio amplifier also, and that is why that particular biasing technique is used for this purposes. Okay, stabilization and all those purposes. The VCC through RC ensures the reverse biasing of the collector base junction, and VCC should ensure that the collector base junction must be reverse biased. That is the transfer operation as an amplifier, isn't it? Then resistance RE ensures the thermal stabilization. I told you. So for thermal stabilization means the temperature raised at the collector base and the base emitter junctions should not affect the operating point. So that is ensured with the proper selection of the resistance RE connected in series with the resistance RE connected in series with the emitter lead. Okay. In series with the emitter lead. So hence resistance RE ensures the thermal stabilization of the circuit and collector emitter voltage VC. It ensures this thermal stabilization and also the collector emitter voltage VC. That is also independent of beta and all beta, that is beta, IGA, all those things now. Okay. Now applying the Kirchhoff's law, Kirchhoff's voltage law, KVL. If you apply the Kirchhoff's voltage law, KVL, at the output side, so you can see that VCC is numerically equal to, that is VCC must be equal to, that is the voltage, VCC must be equal to ICRC, that is if the current flowing through this one is IC, or that is numerically equal to almost equal to IE. So this ICRC plus VCE plus VE is the VCC, isn't it? VCC is the voltage drop across this one, then voltage between collector emitter and voltage across R. That is shown here. That is given here. VCC is equal to ICRC plus VCE plus IER. So this ensures how much value should be taken for RC for it, and how much value should be taken for RE for a thermal stabilization. Okay. So this is what is about the voltage divider bias, and this is also an important topic. So explain the voltage divider bias technique in common emitter amplifier means we have to write down all these features. It's quite simple, I think, and I think you have understood what I have discussed here now. Okay. Now we will see RC coupled common emitter amplifier. When one transistor with its associated circuit is used to amplify the signal, it is called single stage amplifier. That is, if one amplifier, one transistor associated with circuits, that is CE circuits, common emitter circuits, and the RC coupling and all those things, then we say that that is the single stage amplifier, because that amplifier uses only one single transistor and associated circuits. Okay. So when one transistor with its associated circuit is used to amplify the signal, that is input signal, the signal will be a AC signal usually, not DC. DC is for operating conditions to maintain. AC is the signal which is either a audio signal or any other that voltage signals, which is of the order of some audio range and all. Okay. So it is called a single stage amplifier. So an amplifier with associated circuits and one transistor is called a single stage amplifier. If you want to have a multi-stage amplifier, then the single stage output of the single stage amplifier is fed to the input side of the other amplifier stages. Okay, that is what is called multi-stage. So usually in audio amplifiers and video voltage amplifiers, there will be one or two or even three stages for amplification. And we will discuss here only single stage amplifier for the understanding purpose. So to make the transistor as a common emitter amplifier, it is to be operated in the active range. That is base emitter junction forward bias and collector base junction reverse bias. That is the DC condition to be maintained in the transistor circuit. This biasing is done with the help of a voltage divider biasing network R1 and R2 as shown in the figure. In the absence of the signal, only DC voltages are present in the circuit, or DC conditions are maintained in the amplifier. The DC collector emitter voltage VC, the DC collector current IC, and the DC base current IB are the quiescent point of the amplifier. That is Q point of the amplifier. What are the Q point of the amplifier? The Q point of the amplifiers are the collector emitter voltage at the output side of the transistor, then collector current IC of the transistor, and collector current IB of the transistor. That is the base current of the transistor. Okay. On the DC quiescent operating point, we superimpose the AC signals. So where will you connect the AC signals to this amplifier? That is across the base emitter junction. So you connect your signal generator, you connect your audio signal between the base emitter circuit, so that this signal will be superimposed upon the DC condition maintained. So here this is the amplifier circuit. So here the very same R1 and R2 is made here as a voltage divided bias network. RC is there, RE is there, and these are all the coupling capacitors. C in is the input coupling capacitor and CC is the output coupling capacitor. And this C is the emitter bypass capacitor because it bypasses the emitter resistance RE connected in series with the emitter of the transistor. So there are three capacitors used in the output side of the transistor amplifier in the C configuration. That is the C in or C1. You can put anything like that. C1 or C in, that is input coupling capacitor. CC is the output coupling capacitor and C is the emitter bypass capacitor. Okay, and this circuit as a whole will give a single stage amplifier, single stage RC coupled amplifier, and you are giving your input signal between, or you are connecting your signal generator output, that is input to this particular amplifier stage between the base and the emitter. Okay, through this capacitor, so that only AC signal will be passing through the capacitor to block the DC supply or DC current, right? So that it maintains the DC operating condition. So that whatever is the DC voltages available before this particular capacitor in the circuit, then that will never be affected here. Only the DC operating conditions maintained by VCC here for this transistor will be maintained as it is. No DC voltage from any other circuit will be entered here because there is a coupling capacitor connected here. Similarly, only the high frequency output current, amplified output current will be flowing through this one. Because this is also a capacitor which will not allow any DC voltages here to enter into the next stage. If that is the case, what happens? If the DC voltage which enters into the next stage is connected without coupling capacitor, what happens? Then the voltage which applied here will be affecting the operating conditions of the next stage. The next stage operating condition will be changed. So that is why this coupling capacitor actually isolates the input side and output side from DC voltages connected to bias the transistor. Okay, so the transistor will be always, this amplifier will be always maintained its amplification without affecting the subsequent stages of the DC conditions of the transistor of amplifier. Okay, now you give your input signal between the base and the emitter. That is shown here. That's an alternating signal. Right? Now we will see what are those ones. On the DC quiescent operating point, we superimpose the AC signal by the application of an AC sinusoidal voltage. I have shown you now. An audio signal, which is essentially an alternating signal, isn't it? At the input side. Due to this, the base current varies sinusoidally. So when you apply a sinusoidal voltage here, so already the DC conditions are maintained on this transistor for operating in the active region, and along with that particular DC condition, you superimpose this voltage of AC signal with this one. Then what happens? So when the alternating voltage travels on its positive half cycles, then this positive and the DC voltage positive will be added together, so that the positive voltage across the base emitter junction will be gradually increased. Isn't it? So that is what is shown here. So the signal positive half cycle is passing through the, because the signal is an alternating signal having certain frequency, usually a high frequency signal, radio frequency signal. So that signal will be allowed to pass through this scene, that's coupling capacitor. But it should not, it will not allow the DC voltages which is connected to here from the previous stages. Or this transistor will be having the DC operating conditions only through this VCC, which is connected here. That will never change. And that will not be affecting the other subsequent stages because coupling capacitor is here. This voltage will not be reaching to the next subsequent stage because this will block the DC. This will allow it to pass only the amplified version of the alternating signal given to this. Okay. So that is, since the transistor is biased to operate in the active region, this signal is amplified beta times larger than the input current in the common emitter configuration. Very similar we have what we see. Hence, the collector current is The collector current also varies sinusoidally about its quiescent value. Thus, the output voltage varies sinusoidally. The output voltage will be always an inverted amplified version of the input voltage. That you have to understand very well. What is this inverted amplified version? I told you for faithful amplification, whatever is the traversing or whatever is the changes occurring on the signal, input signal, the same kind of changes should be made available at the output signal also. Changing any frequency. Only what you are going to change, you are going to change the amplitude of the signal, the voltage amplitude of the signal. So when you amplify the signal, only the amplitude is varying, the frequency is not varying. So in a C configuration, the output voltage available at the collector emitter region, that is VCE, and that will be an inverted amplified version. That will be an amplified signal version, but that signal is an inverted signal. What does it mean? It means that if you give an AC voltage here, alternating voltage with positive and negative half cycles here, then with the same positive and negative half cycle variations occurring here, the output voltage will be an amplified version with a larger value of amplitude, but it is inverted. Which is inverted means which is in phase but with opposition about what, with opposition of 180 electrical degrees. This is inverted signal. This is the inverted signal because here the signal varies from 0 to maximum means here it varies from 0 to maximum in the reverse direction, the negative direction. If it is going to positive, this goes to negative. So it means that this signal and this particular output signal, this input signal and this output signal has got a phase shift of 180 electrical degrees, or the output signal is an inverted amplified version of the input signal. That is the main feature of the common emitter amplifier or RC coupled common emitter amplifier. The output voltage will be always having a phase inversion or a phase displacement of 180 electrical degrees. Or in other words, the input signal and output signal are in phase but opposition. In phase but opposition. They are in phase, going with the same phase, but it is opposite. When it goes to positive, it goes to negative. That is in phase opposition. Follow my point? Okay. So what are all the important parts here? The transistor common emitter configuration. Resistor R1 and R2 gives the potential divider or voltage divider bias network. It provides necessary DC voltage VCC to keep the transistor in the active region of operation. That is base emitter voltage in the that is the forward bias and collector base junction in the reverse bias junction. And RE, here RE I have just shown you. RE means that is this RE, this emitter resistance RE, because I have given another circuit here, this RE, and this RE is nothing but the same RE you have seen here, this RE. Okay, I just give the letter suffixed here with a small letter because the other figure is having bearing the resistor RE with a small letter, R suffix is small letter. So RE stabilizes the operating point against the temperature variations. The operating point should always lie in the active region of operation for proper amplification. C in and C are called the coupling capacitors. C in and C are called the coupling capacitors. Okay. The function of the coupling capacitors are one to transfer the AC output of one voltage to the input of the next stage, and to provide DC isolation between the first stage and the next stage. So there must be a DC isolation from the first stage to the next stage. Why? Because if there is no DC isolation given, what happens? The DC condition of the first transistor will be connected directly to the second transistor or second stage transistor amplifier. That will change its operating point, and that will disturb the operating point, and that will change the operating point, shift to certain region. So that's why we give coupling capacitors both in the input side and output side. On the input side, the coupling capacitor will allow to pass the input signal of the amplifier, and it blocks the DC. Similarly, on the output side, it allows to pass through the it allows only the output voltage, output signal pass through that particular circuit and blocking the DC voltages, blocking the DC voltages so that the other stages will not be, the 2 point of the other stages will not be affected. Okay, right. Then Cin and Cc are the input coupling capacitor and the output coupling capacitor. I told you the importance of these two capacitors. And the load RL, which is not shown here. The load is actually connected between the output here. Here you connect your load RL. I didn't show it here. And this is the output point of the transistor. That is where you are getting VC. Okay. Now the RL is not shown here. So in this particular case, RL is connected between V out and your this one. Earth. Earth point is common to all, isn't it? So V out and Earth will give the VC. Okay. V out and Earth will give VC. So that's shown here. Okay. So RL is not shown here. Now again, this amplifier circuit I have shown you here. And what is the purpose of this CE, emitter bypass capacitor? What is the purpose of emitter bypass capacitor? It bypasses the AC signal developed across RE to ground. If the emitter bypass capacitor is not there, suppose here RE is connected to the emitter lead, isn't it? Why? Because it has to limit the current through the IC or current IC through RC, and this will ensure a safe current that will not create a much temperature variations on the junction. Or this is a thermal stabilization resistor RE. These are designed, this resistance is designed as per the thermal stabilization needed for the collector based junction and the emitter based junction, while it is offered as a transistor amplifier, isn't it? So when the transistor amplifies signal, this amplified signal will be available here, because the same signal will be passing through emitter also, because IC is almost equal to I told you. So it is not shown here. IC is almost equal to IE. So almost the same current IC will be flowing through the RE, the value of resistance RE, or through the value of resistance RE, or through the emitter lead. So when the transistor is bearing signal, it amplifies signal, then such signal amplification will be taken place, and that signal will be, current signal will be amplified here. The same amplified signal will be flowing through RE also. Then what does happen? When RE is here, and RE of sufficient value is here, that RE will be developing a voltage drop across this one. So your signal current will be dropping across here. So that RE will be having a large voltage drop, reducing the collector emitter voltage. The output will be reduced. When the output is reduced, the voltage gain is reduced. Isn't it? The voltage gain is reduced. So that is why when you apply a signal with a high frequency, then that high frequency signal will be easily passing through CE, the capacitor CE. Or capacitor CE bypasses RE for transferring the signal to earth or common point. From my point, it should not be wasted here. It should not drop any voltage here. Okay, it should be. It will make a short path, short circuit path through CE to the ground. Okay, so that is the purpose of emitter bypass. That's why it's called by emitter bypass capacitor. Okay, and again, when the voltage VC is reduced, means the bandwidth is when the gain is reduced and bandwidth is reduced. Reduced gain means reduced bandwidth. That is the reason. But there should be a compromise between the bandwidth of operation for the transistor and how this transistor is working, how it works. When AC input signal is applied, AC input signal, since it is a alternating signal with instantaneous values. Instantaneous values means the signal will be varying at each instant here. So at this particular instant is having a value amplitude high. This it increases, it has got an amplitude like this. It increases and reaching maximum value, and the amplitude is maximum here. Then it decreases and becomes zero. Then increasing the negative side maximum, then decreasing to zero, and it goes on like this. Follow my point. So at each instant, this amplitude has got a value. That is the amplitude at each instant. That is the instantaneous value of the amplitude. And instantaneous value of the AC signal is represented by the small voltage V and if since it is an input signal, we represent as V in. Okay, so that is shown here. V in, and that V in is the signal voltage that is amplified and between the base emitter terminal, and that is amplified and available between the base emitter terminals. So this V in is applied between base emitter terminal, that is the input terminals of the transistor. Then what happens? Since the base current is increased while IB is while this signal current is increasing, when the signal current increases from 0 to positive maximum, it adds with the DC voltage conditions here, so that the voltage at the base emitter junction will be gradually increased depending upon this variation of signal. Okay, so then what happens? The resistors R1, R2 ensures the proper biasing, that is the voltage divided biasing, and then the resistance RE, which ensures the thermal stabilization of the transistor circuit, so that the transistor's operating point will be always lie within the active region. Okay, when V in varies, the input signal IB varies. I told you the positive half cycle, then the positive DC voltage will be added together. So IB varies. IB increases during the positive half cycle and then decreases to 0 and coming to the negative half cycle it reduces, isn't it? And for a C configuration, we know that the gain, current gain beta is equal to IC by IB. So if beta has large value, which causes the output current IC to increase, and IC flows through the load resistor R. And when this happens, IC is increased and IC flows through the load resistor R, because this is a current that is having a very high frequency current, and that will be bypassed through this and available between the load connected here like this. Okay, that will be available between the load connected here. Okay, now the IC flows through the load resistor, giving an amplified output VC, giving an amplified output VC. And I told you the output voltage is inverted version of the input signal. Why is it having so inverted version means 180-degree phase shift? Why is it so? I told you, and the reason for that one also I explained here. And that is governed by the output loop equation VO is equal to the output voltage VO is equal to VC is equal to VCC minus ICRC. For any CE configuration, output voltage is VO, that is numerically equal to VCE, or the collector emitter voltage, and that is nothing but VCC minus ICRC. If IC is the current flowing through this one, and which flows through this one, then VCC minus ICRC, the voltage drop across this one, will give the output voltage here. If you apply the Kirchhoff's voltage law on the circuit here like this. Okay. So these are all now exemplified, and that are all simplified with the KVL and KCL. Okay, the design is simplified. So that is the reason how the output voltage is varying 180-degree out of phase, or there is a phase shift between the input voltage and output voltage for a C configuration. And the reason is, for positive half cycle of input, when input increases, the forward bias to the emitter base junction increases. Why the input is increased? Because the positive half cycle of the input voltage will be superimposing on the positive voltage of the DC condition, so that the VBE will be increased. So VBE increases means IB is increased. So during positive half cycle of the input signal, the base current increases, so forward bias increases, and junction, that the forward bias increases means junction will be, or the forward base emitter junction will be conducting current more, and this results an increasing collector current. When IB is increased more, IC will be more, that is beta into IB. You know, when collector current increases, the output voltage VCE also the collector. When the collector current increases, what happens? When the collector current increases, ICRC will be increased. So ICRC increased means VO is equal to VC is equal to VCC minus ICRC. If ICRC is increased means VCC minus ICRC will be decreased. So when current is increased from 0 to maximum value, the output voltage is decreased from maximum value to 0, then it goes to negative value. It means that When the output voltage increase from 0 to maximum value, the input voltage or input signal increase from 0 to maximum value, or the signal current increase from 0 to maximum value, the output voltage VCE decreases or increases from 0 to maximum value in the negative direction. Follow my point. When the positive current or the signal current increases, both positive half cycle of the signal current and the DC condition increases the IB. When IB is increased, IC is increased. When IC is increased, VCC minus ICRC is decreased. VCC minus ICRC is decreased, or ICRC is increased. So VCE is decreased. VCE means output voltage. So when IB is increased, base current is increased, output voltage is decreased. It means that when the base current increases from 0 to maximum value, the output voltage increases from 0 to maximum value in the negative direction. Similarly, in the negative half cycle, the same thing happens in the reverse condition. The same thing happens in negative half cycle of the input current. What happens? IB decreases. So IB decreases means IC is decreased. IC is decreased means ICRC, the voltage drop across RC is decreased. It means that the VCE, the output voltage VC is increased. So decreasing IB increases the output voltage. Increasing IB decreases the output voltage. So this is the reason why the output voltage is having a phase shift of 180 degrees or phase inversion, or the output voltage is in phase opposition. That is 180 degree out of phase. Follow my point. That feature you have to note down. Why the output of a common emitter configuration or common emitter amplifier is out of phase by 180 degrees. And this is the reason you have to mention this equation also. And accordingly, you have to make this way. When IB is increased, and IB will be that when the positive half cycle of the signal current, IB is increased. IB increases means IC is increased, ICRC is increased. ICRC increases means VCC minus ICRC, that is VCE or decreases. Means that output voltage decreases. So for increasing input current, decreasing output voltage is resulted. And when the negative half cycle or negative half cycle of the signal of the input current, IB decreases. IB decreases means IC decreases. IC decreases means ICRC decreases. ICRC decreases means the output voltage VC is equal to VCC minus ICRC increases. So with the decrease in IB, the output voltage VC will be increasing. So it is the opposite direction. So that is why the input signal and the output signal will be having a phase shift of 180 electrical degrees, or that two signals are in phase opposition. Okay, that is the phase reverse. That is usually we say that it's a phase reversal. And I told you, since the resistance capacitance network is used to couple between the multi stages of the amplifier, if you want to amplify the signal further with another stage, second stage of amplification or third stage of amplification, then what do you have to do? You give the first stage of amplifier output to the input of the second stage amplifier. Output of the second stage amplifier is given to the input of the third stage amplifier. But in what way you have to give? You have to give the first stage and second stage connected through a coupling capacitor. So this resistance and capacitance network, resistance for biasing resistance network and the capacitance for coupling the capacitor. This resistance capacitance network is used to couple between the multi-stages of an amplifier for improving or for enlarging its gain. What for we use multi-stage amplifiers? In order to improve the gain, so that the output will be a large amplified version of the input. There is no change of frequency, but the amplitude of the signal is increased much. So that is, this coupling of the amplifiers between the multi-stages is taken through resistance capacitance network. That is why the coupling between this capacitor actually makes this transistor to be known as a RC coupled amplifier. Okay, that is RC coupled amplifier. So I think I will just tell about the advantages of RC coupled amplifier and its application. And with this, I conclude this session here. And the same thing will be followed in implementing the RC coupled amplifier in the laboratory. So I will just put an audio for connecting the amplifier leads in what you have to connect the amplifier lead in what places on a breadboard. That will be given to you in a separate video in the ESL 130 Basics of Electronics Engineering workshop. That will be separately given to you. And the video which I took class here now will be available on Moodle for your study on RC coupled amplifiers for your theoretical purpose. Okay. So what are all the advantages of RC coupled amplifier? The frequency response of RC coupled amplifier provides constant gain over a wide range of frequencies. I told you, over wide range of frequencies, the amplifier gives a very good range, a very good gain, and that gain is almost constant, well within the ranges of frequency, and hence most suitable for audio applications because the range of frequencies over which the gain is almost constant. So that this amplifier can be used as an amplifier for audio purpose. Or you can use the C configuration or C amplifier as an audio amplifier. Okay. Then what are the other things? This circuit is quite simple to set up in the laboratory and having only smaller components like small transistors, circuit component resistors, and capacitors. All those things are cheap. So overall cost of the transistor amplifier will be very less. And it is a very compact in shape. So the transistor can be implemented, the transistor amplifier can be implemented on in the laboratory on breadboards in a compact manner, or you can place it on a PCB, that is printed circuit board, in a compact way. And with the upgraded technology, you can still make it as a compact unit for RC coupled amplifier. Okay. Then what are all the disadvantages? The voltage and power gain are low because the effective load resistance of the amplifier is somewhat increased. So I told you the resistance connected or the load means the resistance or whatever is the load which is affected on the transistor output here. If you connect a load resistor here or if you connect another stages of amplifier, then the input resistance of that amplifier or input resistance offered by that amplifier to the output of this amplifier stage is the load of that amplifier, right? And if this amplifier is used, one of its disadvantages is that the voltage gain and power gain of this amplifier will be reduced due to the effective load resistance of the subsequent stages to which it is connected. And sometimes, depending upon the quality of the component used, component means active component like transistors, capacitors, and resistors used. If there is a leakage in capacitance, or if there is certain leakage in the resistance due to usage, continuous use, due to aging or so. So in that case, this amplifier will become, or this amplifier will give a noise, or noise level of the amplifier will be large. So the amplifier output will be noisy. And the third disadvantage which we can say is that due to due to poor impedance matching, the power transfer will be low. Poor impedance matching means I told you impedance matching between the transistor amplifier when it is used as a multi-stage amplifier is very important. The output of the amplifier must be matched, the output impedance of the amplifier must be matched with the input impedance of the subsequent stages of amplifier. If you are using a two-stage amplifier, one amplifier is here, another amplifier is here. The output impedance or output resistance of this amplifier must be matching with the input amplifier in order to ensure maximum power transfer. Why we ensure maximum power transfer here? Because it is the maximum power transfer that ensures how much power will be available at the input of the next stage amplifier to amplify. So the impedance matching must be a criterion in transistor amplifiers design. Or the output impedance of this amplifier or output impedance of an amplifier must be matched with the of the subsequent stages of the amplifier. Or output resistance of the amplifier must be matching with the input resistance. When we say AC signals, we have to take into account the impedance, because for AC signals, impedance is playing into account. We have to take into account the inductive, the capacitive reactance and the resistance altogether. Sometimes, of course, some small inductance may be also there due to the aerial circuits and all those things used in a circuit, in radio circuit also. Then, what are the application of RC coupled amplifier in a wide way? And this is an excellent audio fidelity amplifier, and so that it is very widely used as a audio amplifiers and radios and TVs. It can be used very widely as an audio amplifier because it gives a very good response for audio amplification. And this can be used as a voltage amplifier widely, because audio amplifier means audio signal voltage will be amplified. That's why it's called voltage amplifiers. So RC coupled amplifier can be used as a voltage amplifier. Then, due to poor impedance matching, RC coupling is very rarely used in final stage of amplification. I told you, for amplification purpose, we will be using multi-stage amplifiers. But at the end of the stage, we require to have the power to be improved maximum. Or we should ensure the maximum power transfer at the output of the transistor amplifier. For that purpose, this kind of amplifier cannot be used in the output stage. That is the final stage of amplification. It can be used in the intermediate stage of amplification as a voltage amplifiers or amplifier, pre-amplifiers in the that is audio signal input, pre-amplifier. But at the output stage, we have to use, or we have to choose some other amplifiers, class A, class B type amplifiers, or class C type amplifiers, for giving maximum power transfer at the output side, not to drive the load. Not to drive the load. Load may be a loudspeaker, sometimes having some impedance of some 8 ohm, 16 ohm, like that. Okay, so that is what is it meant by impedance matching of this one. And with this, I conclude the session here now. And next day, next class, we will be discussing about the frequency response RC coupled amplifier. And with that, we will complete the RC coupled amplifier. And these are all quite simple and very easy to understand. And you should learn the circuit by heart. And you should learn all the theoretical aspects by heart, because I have explained to you each and every aspect very, very clearly now. And if you have any doubt, you just tell me. Then we will close the session at this particular point of time. Okay. And thank you very much for your patient listening. Thank you.